Hello everyone, this is Furqan Ahmed. I'm a PhD candidate from IDD Hyderabad, India. The current topic of my research work is called IDD-AW, a benchmark for safe and robust segmentation of drive scenes in unstructured traffic and adverse weather conditions. This work is in collaboration with IDD Hyderabad, the DYSL AI lab in DRDO, and also the iHub data. Now coming to the safety and robustness in autonomous navigation, this has been a major challenge for autonomous navigation from the very start, because this is something where we cannot compromise in developing these autonomous navigation systems. Safety should be paramount, because a small mistake from a machine could actually cost human lives. For example, there have been various numerous incidents that have been reported where nearly 400 crashes were happening by self-driving cars in the US, which is a major debate right now, currently. Uh, there's also Tesla's self-driving technology, which is failing to detect children on the road, and have actually been videos released where it hitting some children, mannequins, or children on the road. And also, California state itself has hit pause on the GM Cruise self-driving cars and have actually called back most of the self-driving cars to its production back. So all these are very important news articles which have actually highlighted the importance of safety and robustness in autonomous navigation. So what we need now is to create proper benchmarks for these robust datasets that are being used for training, and also to design appropriate metrics for calculating safety. So one of the major issues why this is happening is because the datasets that have been used for training these systems may not be as good in the real time when deployed, because there's a lot of challenges when deploying real time. And one of these challenges is driving in very adverse weather conditions. So when you face adverse weather conditions suddenly, when it's not present in the training data, it can cause the system to go awry, and it can cause various damages to the system. So for example, uh, when you take adverse driving challenges in India, there have been numerous incidents where due to heavy rain, there's auto driver and there are a lot of people being killed, and also fog due to low visibility of the roads. There have been many accidents, and this itself. So this is not a new thing. This have been going on for a while, and this is not even in self-driving cars. This is when the people are driving, when there's actual human intervention. So you can see here we also have the road accidents data by weather condition. There's still, even though the sunny clear are there, there's still a very huge amount of accidents happening, upward of 35,000 plus accidents for each condition. And also, these accidents are not just accidents, small accidents, but these have been major accidents, where you can see almost 10,000 plus lives being lost in these road accidents. So this is not a simple thing when it comes to adverse weather driving. Uh, so now the thing is, coming to challenges with these existing adverse weather conditions, is that most of the data that have been there, that is present in available today, is synthetic data. So what happens in the synthetic data is you just take a normal image and you try to apply some kind of rain or fog or condition over it. What happens is, when you do this, uh, there's no real-time data happen. There's no real-time data, so there's no image distortions or some kind of challenges that we see in real time. There's no wiper occlusions or stuff like that. So it's harder to predict these unforeseen circumstances when we actually encounter in real time. Or there's no unstructured traffic, because unstructured traffic doesn't come very often in other countries, in developed countries, fully developed countries. So this could be a major challenge in developing countries like India, where unstructured traffic is always an issue. And most of the data is skewed data set because it's harder to collect data in proper snow or in high fog, because you yourself run the issue of actually collecting the data, and then insufficient sensors and data to actually capture these effects. So you can't just capture these adverse effects through one sensor, and just RGB sensor or just the image sensor to collect this data accurately. All these are very current existing challenges when you come to the adverse weather data sets. So coming to our data set, we have created a benchmark data set for driving scenes in adverse weather conditions and also unstructured traffic. So we have been able to do this by driving around in adverse weather conditions such as rain, fog, low light, and snow. We have made sure to collect conditions in all these images in all these conditions, and also we have made sure to collect a significant amount of images in all these conditions. It's not like we have limited ourselves. Most of the data sets that we currently see don't have that much diversity in terms of uh, their own the roads they cover, or in terms of the conditions. So what we have done is we've collected data from the proper highways and the roads, from the proper traffic roads of Hyderabad to the highways of Delhi to foggy hills of Ooty, and also the snowy mountains of Manali also. So these are all the things that we have collected data. You can, for example, you can see here on the right hand side, we have rain, low light, fog, and snow images. But we also have NIR plus RGB component along with the annotations for this. So this our NIR component actually helps in getting the extra detail in that image, which is you cannot see in the rain, which you cannot see in the just the RGB image. So this extra component actually helps in having better training examples. We'll get to know how this helps and how much effect this makes in segmentation. So when you compare with other state-of-the-art datasets, we have around 202 try sequences, which is much higher than when compared to others. Also, we have 5,000 RGB image pairs, RGB and image pairs, which is again the highest that we have when compared with other same adverse when compared with adverse existing weather datasets. So you can see here these are the number of datasets that we have, which collect which have adverse datasets. So you can see, even though there are a lot of datasets which have correct only images in one condition, like foggy driving, nighttime driving, etc. Or you have Wild Dash or by BRD 100K, where they have images through conditions, but they have very skewed datasets. So ACDCs are most direct uh, competitor dataset. But here also you can see that our dataset actually has more number of label sets, better label set, and also more number of images for each condition. So also higher label set indicating more diversity of this, and also the types of instances when compared to other datasets. For example, when you come to unstructured roads, there's a lot of more diversity in the roads. You can see people, you can see bikes, you can see riders, you can see sidewalks, you can see traffic poles, extra. So there's a lot of extra things that come into picture when you're actually collecting data in unstructured sequences, which are not present in other datasets. And also we have semantic and pixel-wise annotations for each of these images. Coming to the statistics, we actually compare with IDD is another unstructured traffic dataset that have been there, which was collected in India in similar conditions. So even though that has been collected in normal conditions, and our data has been collected in proper adverse weather conditions, where we actually had to go with our car and collect data in heavy rain, fog, snow. We can see here when we actually compare the pixel-wise distribution, we can see it actually compares very well with the current existing state-of-the-art datasets. So that actually means that actually shows the integrity and the quality of a dataset in such a way that this all the classes are present in the dataset as compared with when you actually see in the normal conditions also. Also, it uses scene level hierarchy as the IDD dataset. We take that inspiration because that has uh, a lot of objects being covered. And also it follows the same hierarchical dataset pattern where you can see here there's a 4 level pattern here, 4 level high level hierarchy. So it also follows the same 4 level label hierarchy. This I'll explain why this is important, the label hierarchy, and how we have actually used this label hierarchy to calculate the safety of our dataset. Now comparison with AC, when compared with AC/DC, we actually have higher number of pixel counts per class when compared with AC/DC for most of the important classes. So for example, when you see from person, rider, car, truck, bus, etc., motorcycle, etc., all these are very important classes when it comes to the driving, and we have uh, almost 10 yeah, almost 10 times or 20 times more number of pixels for each of these classes when compared with the AC/DC. This actually shows the quality of our data. Along with that, when you also see number of instances traffic participants per image. So most of the images in AC/DC are maximum they have around you can see the peak of around 4 or 5 instances only per image. But you can see here our dataset actually, even though there are lots of images which actually have instances more than 20 also, which is a very very rare sight in AC/DC. So this makes our dataset that much more challenging, as well as that much more uh, better than existing datasets, and much more better to actually handle real-time scenarios. Now coming to the annotation pipeline, so we have it's a three-step annotation pipeline where we actually extract the frames from the collected data, and we select these frames manually such that both RGB and NR are synchronized for each of these frames, and then we send these frames for pre-processing. So after pre-processing, we send it for annotation, where each image is being annotated according to by experts, and this is again taken through QA peer assessment and then the QA supervisor assessment to make sure there's a two-level quality check happening for each annotation. And then coming to the training part, we actually have a pre-trained model for each of this, and then we do proper quality research into this, and then we actually deploy this model. So it's a very clear annotation pipeline. It's a very clear pipeline for a data set. These are some of the examples of rain data that we have collected. You can see here there's RGB image, the NR image, the annotation, and also the overlay of this. As I said previously, the difference between real-time and synthetic data set, you can clearly see, for example, in the last image, you can clearly see the image of the car auto being distorted here. Even in the rain images or in the last overlay image, you can see here the car at the end is being completely distorted. The car auto here is being distorted, or even in the start, you can see here the bike. You can't even see the proper outline of the bike. So these are some challenges that we have actually faced while collecting the data, and which are actually solving with this data also. Similarly, in fog, you can see very low visibility when it comes to the fog, both in terms of seeing the billboards or even the people on the road. Similarly, for low light also, it's the same kind of situation. And snow, we have actually collected in the snow hills of Manali, where you can actually see the snow right on the roads. This can actually cause a lot of damage when it comes to the uh, safety of driving on these roads. So we have some sample data collection videos you can see here. Uh, this is for the rain that we have collected. You can see it's a very heavy rain data that we have, and we have actually trained and tested on this type of data all through our training to make sure we collect every corner cases. Or you can see the fog data set here, or even so these are the quality of the data that we have collected, and we shows the range of scenarios that we have covered: rain, fog, low light, and also snow. Now coming to the qualitative results, we have actually compared our model with both ACDC and IDD, because ACDC has that adverse weather conditions and IDD has unstructured traffic. So we compare with both of these models, and we can clearly see that, and we use the interimage B framework, which is the state of the art currently for semantic segmentation. So we can clearly see qualitatively that our dataset actually performs very well when compared to both IDD and also ACDC. So you can see here in the second image also, where the ACDC does not even know that there is a road on here, because it cannot properly identify that the rain here. So that is could be a very major challenge in autonomous driving, when you can't even identify that's the road. And also when compared with IDD and IDD-AW, you can see here it has a better classification of people on the road, as well as the sidewalks or uh, the sudden barriers that you have on the road here. It has a much better identification of these, which could actually lead to better safety of the roads, of the driving that we have. So now coming to the MIU for quantitative results, you can see here. So we have the RGB pre-trained on cityscapes, on ACDC, on IDD, and we also have our dataset uh, tested on the RGB trained images, the NIR trained images, and NIR plus RGB trained images. Because we have NIR, we have this quality, or we have this uh, opportunity to actually combine these both two images and actually do this testing. You can see here that our models actually outperform the others by almost 10 to 15% difference in MIUs when tested on the test set of IDD-AW. This actually shows that how well our model is, and how uh, it covers a lot of different scenarios when compared with other datasets. Similarly, we have also done a cross evaluation of these when IDD-AW model is tested on the cityscapes or ACDC or IDD, and their models is tested on our dataset. So you can see here that our model actually performs at least 3% better in each of these conditions. Uh, so it basically shows that our dataset has both inclusivity of in terms of in both adverse weather as well as the unstructured traffic themes. So this was when compared with MIU. Now coming to the metrics of this. Now that we have actually shown the qualitative results of our dataset, and now coming to the metrics of what actually happens behind the validation, what's the problem with it. The traditional approach that we have is the traditional approach of MIO, that is the mean of intersection over union, which is commonly used for evaluating segmentation quality. And now what happens, one of the major challenges of this is it actually does not properly assess the safety of each of these driving scenes. So for example, it actually treats all of the classes regardless of safety significance. When it comes to the driving, there's obviously some classes which are much more important than other classes. For example, you give the importance of identifying the car in front of you much more than identifying a hill which is actually just being predicted on the maybe on the side of the road, or maybe a bird a bird or an animal in the sky. So that is a much less important class when you compare, when you want to predict a person or a rider or a car that is suddenly on the road. So this is not being handled by MIU. Rather, it actually treats all of the classes equal, and also it cannot capture severity misclassifications. For example, a car predicted as uh, a sky, or a person predicted as a sky is much more dangerous than a person being predicted as a rider of a bike. Because a person being predicted as sky, the autonomous vehicle would not stop because it just thinks that it can just go on. Or if it predicted as road, it can just go on. Rather than a person being predicted as a car, where it will actually stop at least when it comes near that person. So even though it's a misclassification, but there's a degree of severity of this misclassification that we need to address. And also that what said, the failure to distinguish between tolerable and dangerous misclassification in real driving scenarios. This is very important, which is not being handled by a current metric of MIO. So what we do is we actually formulate a new metric called safe MIO, where our main objective is to make a more refined metric for safety, and also this overcome the shortcomings which you have just now seen in terms of both severity of misprediction, and also that some classes are much more important to classify than others. Uh, so the significance is actually promotes the safety in driving scenes, which is crucial, and also which considers the safety of these misclassifications and is according to it. So coming to the before defining safe metric, we need to know some things regarding hierarchical labeling. As I've already shown, our dataset actually follows a four-level label hierarchy. When you have a label hierarchy, this actually helps in identifying which classes are the closest or which classes can be tolerable as mispredictions, and which classes cannot be. So when you actually organize it to tree level hierarchy, uh, it's much easier, or it's much safer for us to predict those classes. So what the advantage of this is, it actually creates this inherent semantic relationship between these classes, and also it provides a structured hierarchy for a comprehensive understanding. So what happens is, you're giving a set of extra training to these classes that we are, to these models that we have, and it knows that, okay, fine, it trains better when we say that it should penalize more for this misclassification rather than penalizing for this misclassification. So for example, when you come to the tree distance, So what is the tree distance now? Tree distance is basically the length of the shortest path in a class hierarchy tree. For example, if you want to go from one class to the other, it's the length of the shortest path. And to ensure proper scaling is divided by 2. The purpose of tree distance is quantifies the semantic relationship between classes and also guides the severity of penalties. I'll just show you what the tree distance we mean by this. So for example, consider this our dataset where we have the root dataset, and we have the level 1 where we have the non-drivable things all classified as 1, the living things all classified as 1, and the vehicles all classified as one class, right? And now coming to the level 2 where the vehicles are all again divided as two-wheelers and four-wheelers, and again the large vehicles, and also living things are again divided as person and rider. So we actually show this as three dangerous levels of mispredictions, where first is yellow, which indicates immediate siblings and has tolerable misprediction. For example, if a truck which is identified as bus, or bus being identified as vehicle fallback, it's all terms of large vehicles. So we don't need to penalize it to that level because it still has a tree distance of 1 only. It shows the tree distance of 1. So we actually penalize using that tree distance, which helps in knowing the severity of this misprediction. And now coming to the category 2, where there are some implications of the person being identified as the rider, or a motorcycle being identified as the bus, right? So it's not the same, obviously, but it's still a little bit tolerable when it comes to this, and you have a higher level of penalty. And Red suggests that there's the highest distance and it considers the highest penalty. For example, the motorcycle being predicted as a sidewalk is a very dangerous thing, or a bus being predicted as sidewalk is a very dangerous thing. So these are things that we need to know when calculating safe MIO, and this is how we actually calculate the mispredictions and severity of these mispredictions using these levels of hierarchy. Now for this calculation of safe MIO between for each critical class, so we already know the general definition of MIO is intersection over union. That is the intersection of ground truth and prediction over union of ground truth and prediction. So now coming to the safe classes of calculating safe IOs, we have the intersection of the predicted of the sibling along with the intersection ground truth of the original class, and the union will remain the same, as we all know. So now the final SMIO score is calculated using this formula, where we penalize the original IOU using the tree distance, where D is the tree distance between those two classes of C and S, where C is the original class and S is the sibling class, and S belongs to the C important, where we actually have some important classes because we cannot predict everything as important. So we have taken the set of some classes as important classes, and based on these important classes, we have actually given the penalties and the level of their tree distance. We actually calculate the penalties of this, and then safe SMI complete is basically the summation over all these safe classes divided by the mean of all this I safe, basically. That is SMIO. So now coming to the results of this. So what we do, one thing we do is we do the cross evaluation between various condition experts, between rain, fog, low light, and snow. You can see here when it's only the rain expert, it shows very less on snow. Does not will work very well on snow, and the same happens with the same if it's a very well, if it's performing very well on the fog, it does not perform very well on snow. This is what happens. Basically, we are showing the dangers of using a generalized model in these weather conditions, because you can see very high drop in this when you compare between the models. So now we also calculate between the MIOs and the SMIOs of each of these, where you can clearly see the SMIO of the whole is around like 15%, 10 to 15% lesser when compared to the MIO, and for snow it decreases to almost 25%. So there's a huge drop when compares MIO and SMIO. So for example, a model could have a high MIO, but when it comes to the safety of that model, it might not be the same case. So that's what we're trying to show here, where SMIO is much more important when it comes to the safety of our model being deployed. So we can clearly see that the dangers and discrepancies of this traditional MIO, using this traditional MIO, and also the critical role of this SMIO, which actually helps in knowing the model performance very more accurately in adverse weather conditions rather than just using MIO. Uh, so now we come to class-wise comparison of these SMIO and MIO. This is very important and significant because it actually shows the dangers of misclassifying these crucial classes, especially in driving scenarios. I'll show you. For example, when you see the classes highlighted here between the bicycles, traffic, and sidewalk, you can see here there's a huge difference in huge drops when compared the MIOs and safe MIOs. And also the safe MIO has negative values also, which actually shows the mispredictions, the high level of mispredictions that is being there, uh, and it shows the gravity of the misprediction also. So this is very important when we compare MIO and SMIO, and also the ranges of SMIO ranges between -1 and 1 of MIO, because we are already penalizing based on the tree distance, and we are also dividing based on tree distance. So it will only be between -1 and 1, or when you take the percentage -100 to +100. So you can see here the significant drop of sidewalk, bicycle, and traffic signs, which is not good because bicycles is again a very important class. The sidewalk, you have to be very careful of the sidewalk when you're traveling on the road. Also the same traffic sign. So if you're not able to identify any of these things, it could lead to disastrous results. Uh, and you can see here where I've symbol with red, where there are negative uh, uh, predictions of these classes, negative values of these classes, which shows that the value, for example, in the fog, the sidewalk is around 24, but the same for in SMO is around -48, or even the snow, the bicycle around uh, 0 MIO, but here it shows that it's actually mispredicting all of these bicycles. Because it does not have enough examples, but when you actually have a positive number or a better number, it does not show the severity of these mispredictions. So this actually indicates dangerous misclassifications, which is traditionally overlooked by MIO. And these are very important to address right now, currently, when it comes to the adverse weather conditions. So now we also show with the severity map. For example, if there's a ground truth in the prediction, uh, now a severity map is based on the tree distance that we have. For example, it's predicted as an auto, but there's actually a person here. So we clearly know that this person is very far from being a actual vehicle. So we show that severity map using this red color, where we show that this is a very serious misprediction that we have. And also the other mispredictions that we have are the yellow part that we have in the back here, where the ground truth was actually a vehicle fallback, which is predicted as auto. So that is again a misprediction, which is not the same as the person being mispredicted as an auto. So we give that as a different level of misprediction. We based on the color here. You can see the lowest level is this yellow color, the middle level is the orange color, and the highest level of misprediction is this red color, where it should not have been predicted like this. Similarly, when you see here, there's a vehicle there, but in the prediction, you cannot even see that there's a vehicle. So this could actually lead to disastrous accidents in terms of fog conditions. So we have the severity map here shown, uh, where it should have predicted the vehicle. Uh, Again, you can see that there was there was a vehicle, there's a bike coming from the other side of the road with a rider, which is not even predicted in here. So traditional MIO would actually give just a simple misclassification over it, where it actually should have given a higher misclassification, because even the truck label is different. For example, that is a large vehicle label and this is just a car label. So that is a yellow misprediction. There's a two-wheeler vehicle which not have rated as four-wheeler because the whole patterns of those driving and everything is different. The way you interact with that vehicle is different. And also there's a person here which is very, very dangerous because it does not show in the prediction itself. So all of these are, you can see clearly here that the three levels of misprediction, and which is very clearly being shown here using the severity map and using this SMIO, which is not traditionally we can see using the MIO, where each of this misprediction is giving the same weight, which is not right. Similarly, you see that there's a animal on the road which you will not see in the prediction, but it's actually very dangerous when it comes because animals have very erratic and unresponsive behavior sometimes, and this could actually cause lots of damage. So now coming to the comparison of this model, so we had the quantitative comparison, so now we have the qualitative comparisons here. Uh, for example, you can see here that I'm showing. Uh, you can I'm showing the predictions between differences between statistics, ACDC, IDD, and IDD-AW train model. You can see here that ACDC actually gets very confused when it gets these adverse weather conditions or unstructured traffic. Even Cityscapes does not know where the road margins of the road are, or the IDD dataset, which it does not know because of that it does not have any adverse weather conditions. Whereas our model actually performs much better qualitatively when compared with all of these datasets. You can see the clear clarity of road when there's a wiper coming. It shows that the road is going till there, which is not physically possible. The same as cityscapes, which is not physically possible. The IDW has some adverse weather in it, so it knows that the road ends here, but it still does not know how the rain is coming on the road here, and does not know what to predict there. So again, that's a misprediction here. Whereas in our case, even though there's a wiper occlusion, there's rain on there and everything, it still predicts it pretty well when compared to the other data sets. So in terms of very high unstructured traffic also, you can see our model actually predicts everything with much more clarity when compared to the other models. See, for example, you can see this frame here. Cityscapes actually goes into some kind of random prediction where it does not even know. It seems that the road is going to the sky. And HDC shows that everything is vegetation, or even the road is vegetation. So this could suddenly cause the autonomous vehicle to stop or to suddenly be very erratic in terms of where it doesn't know where the boundaries of the road are, or even the IDD. Whereas our IDD-AW is actually performing much better in terms of uh, predicting this road classifications. Similarly, when you come to the fog conditions, you can see here uh, the cityscapes and IDD does not have very clear indication of where the road is because of the fog. And it somehow so sees that the sky is also the road sometimes and stuff like that, which is not the case in IDD-AW when it comes to that. Or even in the low light, how it's being predicted or being mispredicted. You can clearly see that the margins of the road is very erratic in terms of other datasets, whereas our dataset performs it very well. So, for example, you can see here when it comes to a toll booth, how it's being predicted and how it's being classified. or even in the snow, uh, where because the other datasets don't have that much snow in their datasets, where the snow is on the road, it somehow thinks that everything is either road or everything is the vegetation. It cannot properly identify snow, which is very erratic because snow has a lot of dangerous properties when it comes to where it's on the road, where there's a lot of sliding on the road. There's a lot of uncertainty from the vehicle coming the other way. So these are all the major issues that we have seen, and when we compare these models, this has both this we can clearly show that our model is both qualitatively and quantitatively much better when we compare both along the adverse weather lines and also the unstructured traffic lines. And this could actually be a major game changer when it comes to the autonomous driving in adverse weather conditions, especially in roads like Indian conditions. So in conclusion, we have presented IDD-AW, which is a large-scale dataset, and also benchmark suit for a driving scene is both adverse weather and structured travel conditions. We also present a new metric called safe MIU, which incorporates the safety concerns and not just the accuracy concerns, which is generally the concept of MIU. So it actually takes in the safety concerns based on the hierarchical dataset and based on which prediction to misclassify, and it basically says that all mispredictions are not same, and some mispredictions should be penalized more than the other mispredictions. We also benchmark the state-of-the-art models and show the difference between this traditional ML and SML while considering the important classes. Uh, Now the future work is to find appropriate loss functions and optimize the safe MIO efficiently in the best direction possible.